Hello and welcome to Recurrent Neural Networks in TensorFlow. In this video, we are going to actually give you a flavor of how to implement TensorFlow in a simple application. First of all, we need to understand what are the feature vectors, or sometimes called the embeddings and encodings. And further, we also need to know what kind of different recurrent layers that are available, different kind of layers. And then we will take a simple example, maybe, for example, a text classification on movie reviews, and we will implement that in TensorFlow. So the goal for the text classification application in TensorFlow using recurrent neural networks is not to actually get a very high level accuracy for the classifier. Rather, the goal is to come up with the technique how to, or the flow of the code book, how to actually come up with a code for implementation a recurrent neural network. So just to give you an example, let's say, for example, a text classification example. We have, let's say, a review. This movie is good. I like it. So let's say that's a positive review. Let's say the label is +1. And maybe you can have a lot of different, for example, you may have another review. I hate this movie. Let's say this one, and that might be a negative review. The label is -1, let's say. Now, you may have reviews corresponding to different movies, or maybe for the same movie, or maybe for different movies. And the number of words in that review, they may vary. First of all, we need to come up with a vocabulary. For example, if the reviews are in English language, we need to come up with a vocabulary. So for example, let's say our whole vocabulary is consists of, let's say, 10,000 words. Let's say 10,000 total most powerful or most common words, vocabulary, most important words. Maybe we can have a larger size of vocabulary or smaller size of vocabulary, that depends. Now, in this particular vocabulary, or sometimes called the dictionary, we may have ordering of different words. For example, A appears the first, and maybe the last word is Z, Z-E-Y maybe, or then maybe some unknown word if there is any one. So that might be a vocabulary. And in this particular vocabulary, let's say the word this, T-H-I-S, in this particular vocabulary array, and the word this appears actually, let's say, at index 342. A one-hot encoding for the word this will be a vector with 10,000 components. All the components are 0, but the index 342, that is 1, and all other indices, they are 0. So this is a 10,000 dimensional vector, feature vector, sometimes called as one-hot encoding vector. So the word this will be having one hot encoding vector. The word movie will be having one hot encoding vector. Maybe you come up with this space as a particular occurrence in this vocabulary. In that case, you might be having for this, although the spaces and some stop words, they are removed in pre-processing, but I'm just telling you that for a different language maybe, or for the same language, you may come up with a different kind of vocabulary settings. Similarly, the is will be having one hot encoding and so on. So in this particular case, if we consider this as word 1, word 2, word 3, word 4, word 5, word 6, word 7, then for this particular review, we have 7 one hot encoding vectors, or a sequence of 7 embeddings or encodings. For another review, for this particular review, using the same vocabulary, we will be having this sentence will be encoded to 4 vectors rather than 7 vectors. So for different reviews, we may have different kind of encodings. A more powerful or more effective encoding is actually sometimes known as word embeddings. They are basically used, and we will see shortly in TensorFlow, There are some built-in embeddings that are available, thereby defining, depending upon a language model, they actually define the words that has some sort of similarity. Their embeddings or the dense feature vectors, they are more or less similar with respect to certain definition of similarity. And the words that are not similar, their embeddings or the dense feature vectors, they are dissimilar with respect to certain definition of similarity. So whether you're using one hot encoding or some word embedding or some recent word embedding like BERT from Google AI, at the end of the day, your review or your one instance of your data, it actually will be presented as a sequence of vectors. And those vectors, encoded vectors or embedding vectors, they will be having different length for this particular kind of problem. And these are the feature vectors that we need to process using recurrent neural networks. Also, I need to mention here, for example, let's say you want to have an activity recognition problem in which you have a video and each video have different number of frames. So how each frame will be represented? Well, one common way is to pick each frame and apply some pre-trained convolutional neural network and encode the frame as a feature vector using some um, convolutional neural network trained on, let's say, ImageNet dataset or stuff like so. In that way, each frame will be encoded as a feature vector, and the total number of, or the sequence of this feature vector actually is, this particular video is represented as a sequence of this feature vector. And you can have a different data set. At the end of the day, whatever data set you have to represent that data set as a sequence of feature vectors. Each instance in your training input, in your training data, each instance will be represented as a sequence of feature vectors. And that sequence, the length of the sequence, it will be different for different input for different instances. And that's the case when the recurrent neural network becomes much more applicable. So let's code a simple example, text classification example, where we will be using predefined embeddings, or sometimes just, you can think that embedding as just computing a feature vector corresponding to a word. And for different words, we will be having different feature vectors. And depending upon the length of the words, based on the vocabulary, we will be having the different number of feature vectors for each review. Let's code that in TensorFlow. So let's go in TensorFlow and let's import certain libraries. By the way, if you do not have a TensorFlow installed already, you can work on Google Colab, no problem. So on my machine, I have TensorFlow installed. So I will work on the machine, TensorFlow as TF, import TensorFlow datasets as TensorFlow datasets. So hope everything is working. So it may take a couple of seconds to load these packages. Yeah, the packages are there. You can check the version here of TensorFlow. Right now I'm using 2.3.0. Next we actually import some datasets from TensorFlow datasets. So dataset and the information about the dataset, which actually, this information actually has an encoder or embedder as well, that encode every word to some integer, the encoding. Or you can use a different encoding or embedding as well. So load, let's say IMDB reviews / subworks 8K. That's the data set. And then we have, do we really want to import the encoding as well with info? Yes, and we want to encode that. And then do we need a supervised data set for supervised learning? Yes, supervised, true. True. So that's the data set. It may, there is some error. What kind of error is this? Let me see the error. Let me trace back the error. Return args is maybe the error is failed to construct dataset, server not found. I guess I have messed up with maybe with spellings or something. Let me go back and see. IMDB reviews, REVIEWS reviews, SUBWOR. Oh, these are words, not works. These are words, subwords. Yeah. So it is throwing a warning that it is deprecated. Maybe you have to use encoder separately, but right now I'll be using encoder that is there in this info. So let's now pick the train data set. So let's say training data set as well as the testing data set or validation data set. So validation data set as this data set that we just picked up, and just pick the train out of it, and then data set and just pick the test out of it. So that way we will be having training data set as well as the testing data set. Now we can define our encoder that is there in info. So encoder is equal to info.encoder info.features, text features. We are going to use text features dot encoder. So now you can just think of as this encoder as just it will help us encoding different words and giving the integer indices out of it. So let me, for example, let me write some string. Let's say the string is maybe the string is, let's say, hello, how are you? Let's say that's our string. Let's encode the string into the sequence of integers. Let's say feature vector. Maybe this is not a feature vector. This is just index of. So let me call this as encoded string. That is encoder dot encode, and I want to encode the string. Now, after encodings, you have this encoded string. You can see that encoded string actually. So here is 40258040211320 and all that. You can actually see the vocabulary size of this encoder as well. So for example, what is the vocabulary size of this encoder? Encoder dot vocabulary size. Here, the vocabulary size the encoder is using is 8185 words in the vocabulary. You can also, for example, see which index belongs to which word in the vocabulary. For example, if we just see the, for example, let me for index, let me just for IDX in encoded string, let me just print let me just print which word belong to which format, IDX and encoder dot decode, and here we want to decode it using IDX. So what will happen is we will be seeing different words in our string. So for example, this 4025, that's the index of the word HEL, then 80840, that's the index for 0. So the comma has an index, how are you, these are all the indices. If we change the length of the sentence, we will be having the encoded string will be having different particular length. Now, so after having these encodings, you can think of these encodings as like one hot encodings or indices. Each one hot encoded vector that actually you can just treat as an index in the vocabulary, and then based on that you can build an embedding layer on top of that to compute the dense feature vectors. So after that, let's now go. Now we have our encoder available. Let's now go and shuffle our training data. So let's have or make the batch sizes of our training data. So training data is actually training data dot shuffle. Maybe you want to shuffle our training data with size, let's say 1,000, and we can then make the batch sizes, for example, training data set, as make the batch sizes training data dot padded batch. So here we can define the batch size. Let's say the batch size is let's say 50. That's the batch size, and we also do that on the validation data. So that is validation data dot padded. This is just creating the batches of our original data. So after creating the batch, now we are ready to actually build our model. So let's build a recurrent neural network model. So model is TensorFlow dot Keras dot sequential. That's our model. And here in this particular model, we are going to add different kind of layers. So for example, TF dot Keras, the first layer should be the embedding layer that actually will generate the dense vectors. So embedding layer. So embedding layer will require the total number of vocabulary and the output dimension. What should be the dimension? How many number of feature vectors you really want? The length of the dense feature vectors, embedded vectors. These two arguments are required by the embedding layer. So for example, we set the vocabulary as a vocabulary size of our encoder, and then let's get the dimensions as 10. So we want each embedded vector, each word should be represented as a vector with 10 coordinates, and that should be a dense vector. So that's the start embedding layer that is pretty much doing the feature extraction part of the text data. Then we build tf.keras. Then we build, now our input is ready in terms of feature vectors. Now we can apply a recurrent layer. There are different, variety of recurrent layer. We can apply a simple recurrent neural network, simple RNN layer. We can apply a gated recurring unit. We can apply an LSTM, long short-term memory, or we can apply a bidirectional layer, and inside the bidirectional layer, we can apply the LSTM, GRU, or simple RNN. So let's go with LSTM. So let's go with that. So LSTM. And in LSTM, we have to define the total number of units that is going to be there. Let's define the 10 units. Let's say there are 10 units in LSTM. By the way, there is no connection between this 10 and this 10. You can change, so let me change that to 12 just to get my point clear. I don't want you to get confused with this 10 and that 10. They are completely independent. You can add multiple recurrent layers if you want, just to keep the model simple. I'm now going to add a dense layer, the output layer, the layer towards the output. Keras dot layers dot dense, and let's say this particular dense layer has, let's say, 5 units, just to keep the model simple. And finally, we have the output layer for softmax, which has just 1 unit because it's a binary classification problem. So let's say this is our model, and if everything is fine, the model is there. Next, we compile our model. So model dot compile, and there we set different kind of attributes. For example, we set a loss function, which is tf dot keras dot losses. Let's set it as a binary cross entropy loss, and let's set the from logits as true. And further, we actually set the optimizer as tf dot keras dot optimizers, and let's set Atom there. Yeah, Atom with whatever default learning rate. So let's set the default learning rate, or maybe maybe we can set a learning rate. So let's set the learning rate 1e minus 3. Let's say that's the learning rate. And then finally we set the matrices, the metric as, let's say, accuracy. So that's our model. The model is ready, and now we are ready to actually fit our model. So history is model.fit, training data set, number of epochs. I'm just setting 2 epochs now because it will take longer to actually converge. Validation data, let's say validation data is validation data, and validation steps, how many steps are there? So validation steps, I should have broken down that to, let's say validation steps are, let's say 30 or 20 or whatever. So now it will start training. There are 2 epochs that it will go through. The important part here is actually this model, because that's the whole crux. And even in that model, if you see, the first layer, embedding layer, is actually acting as, just you can think of as a feature extractor, and arranging the feature vectors in a sequential way. And then the main core part of recurrent neural network is the recurrent layer here, which right now we are using as LSTM. But you can use that. You can use here a gated recurrent unit, which is more recent and actually more popular as well. You can use a simple RNN here, RNN layer, which is just a layer of a lot of perceptrons. Or you can use a bidirectional layer, and inside the bidirectional layer, you can set the recurrent units to be LSTMs or GRU or simple RNNs, whatever. So it is taking, it will take maybe a couple of minutes. So let's, and by the way, once you have set your recurrent neural network model true, rest of the story is almost the same with all, like whether it's a convolutional neural network or a plain neural network, the training part and all that stuff is almost the same. One more thing, we could have omitted this layer. This layer is not a recurrent layer. This is the layer towards the output, and that's the final layer. We might have omitted this layer as well to just make the model much more simpler, maybe at the cost of accuracy. But I mean, what we cannot avoid is the embedding layer. This is unavoidable. Recurrent layer in this is unavoidable, although we could have used GRU or something else. And then the final layer, that is unavoidable. Maybe we could have avoided this if we really wanted to. But that's whole the idea of how to design a recurrent neural network. So let's wait it for to complete the 2 epochs. So let's wait for it. And so it has trained just 2 epochs. I've set 2 epochs just for the training to complete quickly, and I have not made the model too complicated, just again to complete the training quickly. So you might be seeing training loss and validation loss might be a little higher, but that's fine. I mean, I guess you get the idea that we can play with different parameters too, because the goal is not the classification. The goal is to understand the recurrent neural network, how to implement that. Further, you can have this training loss, validation loss, and validation accuracy using this model.evaluate. And there you can give the validation data. And not only, it is actually computing the validation loss and validation accuracy. And once done, you can then print the validation loss as well as validation accuracy. This validation loss and validation accuracy might be pretty much the same as here, because that's the same training data. And now these are a lot of batches. Actually, these are 500 batches with the batch size. We set the batch size earlier, I guess, as 50. So these are 500 batches of the total training data on which it is evaluating. So it may take a couple of more seconds to complete. Yeah, it's about to complete. So yes, it is almost the same as already reported, like so. Um, so that's how you can build a model. So everything in here in TensorFlow is the same, except how you define a recurrent neural network model. In other frameworks, for example, in MaxNet and PyTorch, there is a separate RNN module that is used to define the recurrent neural network. But here in TensorFlow, you can just go directly, just like you define the ordinary plain neural networks. You can add recurrent layer there.